We start this lecture with an overview, a plan for what will be presented. This pre-lecture introduces two important new concepts, kinetic energy and work. These concepts are defined in terms of the fundamental concepts from dynamics, force and mass, and kinematics, displacement and velocity. We will find that integrating Newton's second law through a displacement will result in an equation that links these two concepts of kinetic energy and work. This equation, called the work-energy theorem, or sometimes the center of mass equation, allows us to easily answer many questions that would be very difficult using Newton's second law directly. We'll start our introduction of work and energy by considering the simple one-dimensional situation shown. A force is applied to an object, causing it to accelerate. We say that the force acting over time causes the change in velocity. We can quantify this statement by integrating the force over time to obtain the relationship between this integral of the force over time and the change in velocity. We could also describe this situation by saying that the force acting through a distance caused the change in velocity. How do we quantify this description? Well, consider the motion at time t. In the next instant of time, dt, the velocity will change by an amount dv, which is equal to the acceleration times dt. In this same time dt, the position will change by an amount which is equal to the velocity times dt. We apply Newton's second law to replace the acceleration by the net force divided by the mass, and then combine the equations to eliminate dt and obtain the equation shown. If we now integrate this equation, we obtain the relationship between the integral of the net force over the displacement and the change in the square of the velocity. We define the integral of the force over the displacement to be the work done by the force, and the quantity 1/2 the mass times the velocity squared to be the kinetic energy of the particle. Thus we see that in one dimension, the work done on the object by the net force is equal to the change in that object's kinetic energy. Work and kinetic energy both are measured in joules, where 1 joule is defined to be 1 Newton meter. We will do a simple example on the next slide that illustrates the use of these concepts. Here we see a box of mass 6 kilograms that is initially at rest. A horizontal force of magnitude 24 newtons is now applied and the box begins to move. We would like to determine the speed of the box when it is at a distance of 8 meters from its initial position. How do we go about making this calculation? Well, we could first use Newton's second law to determine the acceleration, and then use this acceleration in one of our kinematics equations to determine the time it takes to travel 8 meters, and then use another kinematics equation to determine the speed at this time. There is, however, an easier way. Namely, we can simply equate the work done by the net force, which is just the applied force in this case, to the change in the kinetic energy of the box. Now, since the applied force is constant, we can take it outside the integral, and then the work done is just equal to the product of the applied force and the distance. Since the box was initially at rest, the change in kinetic energy of the box is just equal to its final kinetic energy. Consequently, we see that the final speed is equal to 8 meters per second. We've just seen how helpful this connection between the work done and the change in kinetic energy in one dimension can be. In order to generalize this connection to more than one dimension, we will need to first introduce the concept of the dot product of two vectors, which we will do on the next slide. So far, all operations we have performed on vectors have produced another vector. When we add or subtract vectors, the result is another vector. When we multiply a scalar by a vector, the result is also a vector. How do we multiply two vectors? Well, there are actually two different products of two vectors. The cross product of two vectors produces another vector, and we will discuss this operation later in the course. Today we will introduce the dot product of two vectors, which produces a scalar. The dot product of any two vectors is defined to be the product of the magnitudes of the vectors and the cosine of the angle between them. Therefore, if the two vectors are parallel, the dot product is equal to the arithmetic product. If the two vectors are perpendicular, the dot product is equal to 0. If the two vectors are anti-parallel, the dot product is equal to minus the arithmetic product. The dot product of two vectors is a measure of the projection of one vector along the other. The dot product is used to define the components of vectors. For example, a sub x and a sub y are the dot products of A with the unit vectors in the x and y directions respectively. Here we see two vectors, a and b, defined in terms of their x and y components. If we now take the dot product of these two vectors, we see that the only terms that survive are the products of the same components. In the next slide, we'll use the dot product to define the work done by a force. A couple of slides back, we determined that in one dimension, the integral of the net force over the displacement of an object is proportional to the change in the square of its velocity. We will now make use of the dot product to generalize this result to more than one dimension. We start by defining the work done by a force on an object as the integral of the dot product of the force and the displacement. We can see from this definition that only the part of the force that is parallel to the displacement contributes to the calculation of the work done by the force. For example, if you pull a box across a horizontal frictionless floor, both the weight and the normal force are perpendicular to the displacement, so that neither of these forces does any work on the box. Only the tension force has a component in the direction of the displacement, so only the tension force does any work on the box. We'll now look at the box being pulled up a frictionless ramp so that we have displacements in two dimensions, x and y. We can now basically repeat the derivation of the one-dimensional case for each component. That is, we start from the equations for the change in velocity and displacement during a time dt. Once again, we apply Newton's second law to replace the acceleration by the net force divided by the mass and combine the equations to eliminate dt and obtain two equations, one for each dimension. We now integrate each equation and add them to obtain our final result shown. The left-hand side of the equation is equal to the change in kinetic energy of the box. The right-hand side of the equation is the work done by the net force, since the dot product can be expanded as the sum of the products of the components. We now see that defining the work in terms of the dot product of the force and the displacement allows us to generalize our one-dimensional result. The change in the kinetic energy of an object is equal to the work done on that object by the net force. We call this statement the work kinetic energy theorem. On the next few slides, we'll explore the work done by several forces. Here we see a mass m being moved along some arbitrary path connecting two fixed points near the surface of the Earth. We want to calculate the work done by gravity along this path. We will first approximate the path as a series of infinitesimal straight line segments along the horizontal and vertical directions as shown. Now, the work done along all of the horizontal segments is 0, since the force, the weight, is always perpendicular to the direction of the horizontal segment. Therefore, the total work done by gravity along this path is just the sum of the work done by gravity along the vertical segments. Since the force, the weight, points down and the vertical segment, dy, points up, the dot product of these two vectors is equal to minus mg times dy. Therefore, the total work done by gravity along the path is just equal to minus mg times the total vertical displacement delta y. Note that this formula we have just developed for the work done by the weight does not depend on the path taken, but only on the difference in height of the initial and final points. When the work done by a force during some motion only depends on the endpoints of the motion, but not on the details of the path, we say that the force is conservative. A consideration of conservative forces will lead us to the important concept of potential energy in the next lecture. To illustrate the power in the work kinetic energy theorem that is realized with conservative forces, we will do an example on the next slide. We'll now use the result for the work done by the weight in an example that illustrates the power of the work kinetic energy theorem. Here we see two balls released at the same time from the same height h. One ball simply falls with constant acceleration g. The other skids down a frictionless, curved surface. The free fall problem is one we've solved many times. We know the ball's velocity and position at any time. We use this information to determine how long the ball is in the air and with what velocity it hits the ground. The skidding ball looks to be a much more difficult problem. The net force here is certainly not constant. Therefore, we cannot use our kinematic equations for constant acceleration. Indeed, finding the position and velocity of the skidding ball at any time is difficult. However, we can use the work kinetic energy theorem to easily find the final velocity. Only two forces act on the skidding ball: the normal force provided by the surface and the weight of the ball. Now, the ball always moves parallel to the plane. The normal force is always perpendicular to the plane. Therefore, the work done by the normal force, given by the dot product of the normal force and the displacement, is zero. Consequently, the work done by the net force here is just equal to the work done by the weight, which is equal to minus mg delta y. Applying the work kinetic energy theorem, we see that the final speed of the skidding ball is just equal to the square root of 2gh, the same as the final speed for the dropped ball. We will close this pre-lecture with a discussion of two more examples of the work done by conservative forces. We have calculated the work done by the weight, a constant force, when the orientation of the path relative to the force was changing. We will now calculate the work done by a spring in one dimension. In this case, the orientation of the path relative to the force is simple, but the magnitude of the force changes as we move. If the coordinate system is chosen such that x equals 0 is the relaxed length of the spring as shown, then the force exerted by the spring on some object attached to its end as a function of position is proportional to the extension or compression of the spring. As we move the object between two positions, x1 and x2, the force on the object clearly changes. Breaking the movement into tiny steps, we see that the work done by the spring along each step will depend on the position. To find the total work done, we need to integrate this expression between x1 and x2 and obtain the result shown. Here we see a plot of the force as a function of displacement as the spring is moved from x1 to x2. The area under the curve represents the work done by the force. Note that the formula for the work done by a spring that we just derived depends only on the endpoints of the motion, x1 and x2. In fact, if we first stretch the spring from its equilibrium position, we see that the spring force points in the opposite direction to the displacement and therefore does negative work. If we then compress the spring back to its equilibrium position, the spring force has the same direction, but the displacement is now in the opposite direction, so that the spring force does positive work. In fact, the magnitudes of these negative and positive works are equal, so that we see that when the spring is returned to its original position, the net work done is 0, the signature of a conservative force. As a final example, we will consider the work done by gravity on an object of mass m that moves in 3 dimensions along some arbitrary path between two fixed points, r1 and r2, that are far from the surface of the Earth. In this case, both the direction of the path relative to the direction of the force, as well as the magnitude of the force, can change along the path. The magnitude of the gravitational force that the Earth exerts on this object is given by the universal gravitational force law. The direction of this force is always radially inward towards the center of the Earth. Once again, we break the path between R1 and R2 into tiny steps. For now, just consider one of these steps and realize that it can be broken into two even smaller steps, one that is parallel to the radial direction and one which is perpendicular to the radial direction. Since the force is radial, the work done when moving along the perpendicular step is 0. The work done when moving along the radial step is just equal to the force at that point times the radial displacement. The total work is therefore just the sum of the work done by all the radial steps as shown. To make this sum, we do the integral and obtain our result, that the work done by the gravitational force as an object is moved from R1 to R2 is proportional to 1 over R2 minus 1 over R1. We conclude with a brief discussion of the main points of this prelecture. First, we defined two new concepts that are represented as scalar quantities. The kinetic energy of an object is defined to be 1/2 the product of the mass of the object and the square of its velocity. The work done by a force as an object moves between 2 points along some path is defined to be the integral of the dot product of the force with the displacement along the path between those 2 points. Second, we integrated Newton's second law to obtain the work kinetic energy theorem, that the work done by the net force on an object as it moves between 2 points is equal to the change in its kinetic energy. Third, we determined that the work done by the gravitational force, both near the surface of the Earth and more generally between any two objects separated by any distance, and the work done by the spring force do not depend on the path used to evaluate the integral and are therefore examples of conservative forces.